Okay, in this video we'll be talking about why the component of gravity down an inclined plane is equal to mg sine theta. Okay, so first things first, let's add our forces that are acting on our object at this moment. So we have our weight force, right? Going directly downwards. We have a normal force, which is perpendicular to the surface. So Fn. And obviously, as it's sliding down, there is some kinetic frictional force acting in the opposite direction that is going in. So if we take these forces and chuck it in a free body diagram, we can say that we have our weight force going down. Right, we have our normal force going up this way. If normal, then we have our frictional kinetic force acting this way. If we draw a traditional X and Y axis like this, down like this, so that's X and that's our Y axes, you see we only have the weight force acting on this coordinate system. We have the friction force and the normal force not aligned with the coordinates. But if we draw a tilted coordinate system like this, so we see we just rotated it up like this, so this is now the Y, and this is now the X, we now see we have the normal force and the frictional force acting on the X-axis. Normal force acting in the positive, frictional force acting in the negative direction. So now, if we draw another diagram, we have our Fn and we have our Fk. And this means we have two components of our weight force. One of these is mg sine theta, and the other is mg cosine theta. We don't know which one's which. That's what we're trying to find out. If we compare these two diagrams together, you can see the weight force is just being distributed by these two vectors on the bottom diagram. So if we redraw this, we can say that this weight force down there is equal to these two vectors together. Right? So we see how we just move this one over here, and then move this over here. And then obviously that is just that. Okay, so again, one of these is mg cosine theta, and the other is mg sine theta. We don't know which one's which. So in order to figure out which one is which, we need to say is either this is theta or this is theta. Which one's which? We don't know. That's how we figure it out. So to figure it out, let's draw our incline again. We'll draw it much bigger this time. This is again theta. And we have our object. Let's just draw it as a dot this time. So the center of mass. If we draw our component straight down, we have a right angle here. And we draw a line perpendicular to the surface. We also have another right angle here as well. Right? And this is also a right angle. So this angle right here is equal to 90 minus theta. The reason for this is because all angles in a triangle equal to 180 degrees. Therefore, we have a 90 degrees here. So that's equal to 90 degrees plus theta plus whatever this is, which we'll just call 5 for now. Right? So plus 5. So that means if we do some maths, we can say that 90 is equal to theta plus 5. And so 90 degrees minus theta is equal to 5, which is what we get here. So as we know that this whole thing is equal to 90 degrees, and if this angle here is 90 minus theta, that means that this angle here has to equal theta. So what this tells us is on this vector diagram here, this angle must be theta. So what that means, geometrically speaking, if this is Fw, which is just mg, if we use our sine rules, we know that this is the opposite side, and we have our hypotenuse, so therefore this must be mg sine theta this way. And therefore this must be mg cos theta, as this is the adjacent side, and we have the hypotenuse. So what we find is the component of velocity going into the surface, which is over here, is mg cos theta. And this component of gravity, which is going down the incline, is equal to mg sine theta. And that is how gravity down the incline is derived as mg sine theta. Hopefully that helps.